Good afternoon, everyone. Welcome to week 4 assignment solving session. Today I'll be discussing some of the questions related to week 4 lecture materials and the solutions to week 4 assignment questions. So let's start. So the first question is lithium shows the highest reducing power in an aqueous medium due to the option 1 low sublimation energy of lithium, 2 high hydration energy of lithium ion, 3 lowest ionization energy of lithium, and 4 small size of lithium atom. So let's go through each statement. First one, low sublimation energy of lithium. So lithium is a solid at room temperature and has a really high melting point compared to other elements in the same group, and sublimation energy is also really high. So while moving down the group, the sublimation energy decreases compared to lithium. So the statement is wrong. And second one is high hydration energy of lithium ion. So lithium plus ion has highest hydration energy compared to other elements in the group because it's a small size. It has high charge to radius ratio compared to other elements. So reducing power increases with increasing hydration energy. So the statement is correct. And third one is lowest ionization energy of lithium. Uh, so when you move down a group, ionization energy decreases, that we know. So in the group, lithium is in the top, then sodium, potassium, rubidium, cesium, and francium. So when moving down the group, ionization energy decreases. So lithium has the highest ionization energy in the group. So the statement is wrong. And next one is small size of lithium atom. So because of the small size, it will have high hydration energy, and hydration energy is proportional to the reducing power. So the statement is correct. So the answer is option B. Statement 2 and statement 4 are the correct ones. Next one is the main oxides formed on combustion of lithium, sodium, and potassium in excess of air respectively are option A is lithium oxide, sodium oxide, and uh, potassium superoxide. Next one is lithium oxide, sodium peroxide, and potassium superoxide. C is lithium superoxide, sodium oxide, and potassium oxide. And option D is lithium oxide, sodium peroxide, and potassium oxide. So, we need to know what are the properties of each element, like when each element is exposed to air. So, in the group, lithium forms only oxides, that is lithium oxide. So lithium plus O2 is given. It's not chemically balanced. So next one is sodium. Sodium exposed in air will give sodium peroxide and sodium oxide. And next one is potassium. Potassium in air will give superoxides, that is KO2. Then there is rubidium and cesium. They are also reactive with oxygen, and they will also give superoxides. So rubidium plus oxygen will give rubidium superoxide, and cesium. So, how we distinguish between oxide, peroxide, and superoxide? So, these alkali metals, when they are in uh, cationic form, they will have positive charge. So, for example, in lithium oxide, lithium is in positive charge. So, there are two lithium and one oxygen. So, when we balance this charge, there is 2 plus charge here because 2 lithium are there. So, oxygen will be 2 minus. So, O2 minus is oxide. And next one is peroxide. For example, in Na2O2, here sodium is in plus 1 state and 2 uh, sodium are present, so it will be 2 plus. So, we need to balance the oxygen charge. So, there are 2 oxygens. So, to cancel 2 plus, you will need 2 minus. So, if we give one negative charge to oxygen, there are 2 uh, O negative. So, that will cancel out. So, it is O minus, which is peroxide. And next one is superoxide, where potassium and oxygen. So, potassium is in plus charge, plus 1, and total O2 charge will be negative. So, there are 2 oxygen. So, it should be 1 oxygen should be minus half. So, 2 into minus half will be uh, minus 1. So, that charge will cancelled out with 1 positive charge. So, O minus half is superoxide. So, the question was the main oxides formed on combustion of lithium, sodium, and potassium. So, lithium forms lithium oxide, uh, sodium forms both peroxide and oxide, and potassium forms only superoxide. So, the options are uh, option B will be the answer because sodium mostly prefers to form sodium peroxide. So, option B is the answer. Question 3 is a metal M reacts with N2 to form compound M3N, and M3N on heating at high temperature gives back metal M, and M3N on heat reacting with H2O gives a gas A, and A turns blue color on passing through copper sulfate solution. So, what is M and A? Options are A, lithium and NO2, B is sodium and NO2, C is sodium and ammonia, D is lithium and ammonia. So, we are given M plus N2 giving M3N. M plus N2 giving M3N. So, this is reduction of nitrogen from 0 state to minus 3 state. So, in group 1 elements, we can lithium reduces nitrogen to M3N. So, 6 lithium will react with 1 nitrogen molecule to give 2 molecules of Li3N. So, we know that when lithium nitride, that is Li3N, is reacted with water, it produces hydroxide and liberates ammonia gas. So, Li3N plus 3H2O will give 3 lithium hydroxide and ammonia gas. So the question was, what was M and A? M, we know lithium, and A is the ammonia gas. So option D is the answer. Next question is, with respect to the following trend, the correct option is 1. A melting point is in the order of sodium fluoride greater than NaCl greater than NaBr greater than NaI. Second one, stability of peroxide is in the order of sodium peroxide less than potassium peroxide less than rubidium peroxide less than cesium peroxide. And 3 is basic strength of oxides is in the order of cesium oxide less than rubidium oxide less than potassium oxide less than sodium bicarbonate less than lithium oxide. And fourth one is stability of bicarbonate is in the order of lithium bicarbonate less than sodium bicarbonate less than potassium bicarbonate less than rubidium bicarbonate less than cesium bicarbonate. Okay. So let's go through each option. So given the melting point order, and so the melting point depends on the ionic character of the molecule. Higher the electronegativity difference between a cation and anion, the higher will be the ionic character. So here it's given halides of sodium. So in the halide group, when we move down the group, the electronegativity decreases. So fluorine has the highest electronegativity. Fluorine greater than chlorine, greater than bromine, greater than iodine. So when we move down the group, electronegativity decreases. So when we form an ionic compound with sodium, highest electronegativity difference will be for sodium fluoride. So sodium fluoride forms ionic compound which has more electronegativity difference compared to sodium chloride and bromide and iodide. And with increasing in ionic character, the melting point increases because they become more crystalline in nature, ionic crystals. So the order of melting point will be the same order. So sodium fluoride greater than sodium chloride greater than sodium bromide greater than sodium iodide. So this order is correct. And next one is stability of peroxide. Sodium peroxide less than potassium peroxide less than rubidium peroxide less than cesium peroxide. So we have already discussed in the previous question the formation of oxides where sodium prefers to form peroxides, but potassium, rubidium and cesium prefer to form superoxides. So the order should be in reverse because sodium forms peroxides. So it should be sodium peroxide stability greater than potassium peroxide greater than rubidium peroxide greater than cesium peroxide. So this one is wrong. And the next one is basic strength of oxide. Uh, um, we have already discussed similar one where lithium preferred to form oxide. Then sodium also forms both peroxide and oxide. These three form only superoxide. So the order is right. And fourth one is stability of bicarbonates. Lithium bicarbonate less than sodium bicarbonate, less than potassium bicarbonate, less than rubidium bicarbonate, less than cesium bicarbonate. So the stability of bicarbonates decreases when we move down the group. So the order is wrong. The order should be uh, lithium bicarbonate greater than sodium bicarbonate greater than potassium bicarbonate greater than rubidium bicarbonate greater than cesium bicarbonate. So we are asked to find correct option. So statement 1 and 3 are right. So correct answer is option C, 1 and 3. The next question is, in the solid state, methyl lithium exists in option A, dimeric form, B, monomeric form, C, dimeric as well as monomeric form, and D, tetrameric form. So in the solid state, lithium, methyl lithium exists in tetrameric form because LiCH3 it's considered as an electron deficient species, so it does association and forms tetramer, and it is synthesized as follows: 2 lithium plus CH3Cl or CH3Br, and in dry hydrocarbons or dry ether. And it will give methyl lithium and lithium chloride. So the tetramer exists in, I'll draw the tetramer. So each lithium is present on the alternate positions. So so 4 lithium and CH3 also in the alternate position. CH3. So this will be the tetramer of methyl lithium. The next question is the solubility of alkali metal hydroxide follows the order. So option A is lithium hydroxide greater than sodium hydroxide greater than potassium hydroxide greater than rubidium hydroxide greater than cesium hydroxide. B is lithium hydroxide less than sodium hydroxide less than potassium hydroxide less than rubidium hydroxide less than cesium hydroxide, and C is lithium hydroxide less than sodium hydroxide greater than KOH less than rubidium hydroxide less than cesium hydroxide, and D is lithium hydroxide greater than sodium hydroxide less than potassium hydroxide greater than rubidium hydroxide greater than cesium hydroxide. So the increasing order of ionic character, sorry, yeah, the ionic character of metal increases down the group. So the solubility of hydroxide increases down the group. So ionic character of metal is directly proportional to solubility. So the order of the metals in the group is lithium, sodium, potassium, rubidium, and cesium. So when we move down the group, ionic character increases because moving down the group, ionization energy decreases. So it's easy to remove the electron. So uh, it can become ion easily. So ionic character uh, increases while moving down the group. So solubility increases. So cesium has solubility order will be the reverse. So cesium hydroxide will be higher than rubidium hydroxide, potassium hydroxide, sodium hydroxide, and uh, the last will be lithium hydroxide. So option B is the answer. The next question is the correct order of solubility of potassium chloride, uh, potassium bromide, and potassium iodide in water is option A is potassium iodide less than potassium bromide greater than KCl. Uh, Option B is KCl greater than KBr greater than Ki. C is Ki greater than KCl greater than KBr. And D is Ki greater than KBr greater than KCl. So similar to previous case, the increasing of ionic character will be KCl greater than KBr greater than Ki, because uh, Cl will be highly electronegative compared to bromine and iodine. So the electronegativity difference will be high for KCl, then KBr, and Ki. So this will have highest ionic character because of electronegativity difference. And this will be potassium iodide will be having lowest. So KCl will form ionic solids, and the order of lattice energy will be same order. Uh, so if a molecule has highest high lattice energy, it means that the molecule will be highly stable and less soluble. So the order of solubility will be the reverse order. Uh, lattice energy is inversely proportional to order of solubility. So the answer is Ki greater than Kbr greater than Kc. So it's option D. The next question is the incorrect statement is option A. All alkali metal salts impart characteristic color to Bunsen flame. B is among lithium hydroxide, cesium hydroxide, potassium hydroxide, sodium hydroxide, and rubidium hydroxide. Cesium hydroxide has the highest solubility in water. And C is among the alkali metals, cesium is the most reactive. D is the reducing character of alkali metal hydride. Follow the order: lithium hydroxide greater than sodium hydroxide greater than potassium hydride greater than rubidium hydride greater than cesium hydride. So let's go through each option. So first statement is all alkali metal salts impart a characteristic color to Bunsen flame. So we know this one where all the alkali metals are having one electron in its s orbital. NS1 configuration. So when we um, put the salt in Bunsen flame, the valence electron excites and goes to p orbital. So when it gets excited, it absorbs some energy and uh, releases uh, energy in the visible region. So the flame will be having a characteristic color. So lithium will be crimson red, sodium is golden yellow, potassium is violet, then rubidium red violet, and cesium is blue. So option A is correct statement, and B is among lithium hydroxide, cesium hydroxide, potassium hydroxide, sodium hydroxide, and rubidium hydroxide. Cesium hydroxide has the highest solubility in water. So when we move down the group, the ionic character of the metals increases, so highest solubility also increases. So this statement is correct. And next one is among the alkali metals, cesium is the most reactive because alkali metals are we know it has NS1 configuration, and when we move down the group, its ionization energy decreases. So lithium, sodium, potassium, rubidium, and cesium. So when we move down the group, ionization energy decreases. So it will be easier to remove one electron from cesium than lithium and other elements. So cesium will be highly reactive because it can donate that one pair of electron to other elements. So option C is correct. And option D is the reducing character of alkali metal hydride. Follow the order: lithium hydride greater than sodium hydride greater than potassium hydride greater than rubidium hydride greater than cesium hydride. So the ionization energy decreases down the group. So hydrogen can be removed as H minus, and H minus can behave as reducing agent. That is uh, the same character only. So the ionic character will be So in this series, moving down the group, the ability of central metal to become cation increases. So it will give one of its electron to hydrogen, so it can become hydride. So this hydride can act as a reducing agent. So the reducing character of alkali metal hydride will be in the order lithium hydride less than sodium hydride less than potassium hydride less than rubidium hydride less than cesium hydride. So this will be the order, but the reverse order is given. So statement D is wrong. So the answer is option D. Next question is the option showing the correct reaction among the following are. Option 1 is 2 lithium plus alkyl halide in dry ethanol. ETOH is ethanol. Okay. So ETOH is ethanol. So 2 lithium and alkyl halide in dry ethanol giving uh, alkyl lithium and lithium halide. Second option is 2 lithium and alkyl halide in dry methanol giving alkyl lithium and lithium halide. Option 3 is 2 lithium and alkyl halide in dry hexane or pentane giving alkyl lithium and lithium halide. Option 4 is 2 lithium and alkyl halide in dry uh, uh, triethoxyethane and or THF giving alkyl lithium and alkyl halide. So formation of lithium halide and alkyl lithium is the reaction. So let's write down the reaction. 2 lithium and alkyl halide in dry ether or dry uh, hydrocarbon giving uh, alkyl lithium and lithium halide. So this is the uh, reaction. Dry ether or dry hydrocarbon are used. So here dry ethanol and dry methanol is used. So these are not the correct ones. And in the third one, dry hexane or pentane is used. So they are hydrocarbons. So this one is right. And in next one, dry 82 ethoxyethane or THF. They are ethers. So Et2O is so this will be Et2O, and THF is tetrahydrofuran, will be this. So these are ethers. So these uh, third one and fourth one are the correct reaction. Next question is among the alkali metal hydroxide, the strongest base is. Option A is rubidium hydroxide, B is lithium hydroxide, C is sodium hydroxide, and D is potassium hydroxide. So among the alkali metal hydroxide, basicity increases from top to bottom because the ionic character of the metal increases due to low ionization. So in the group lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, these are the given ones. So when we move down the group, basicity increases. So option A is the correct answer. Next question is the treatment of sodium hydroxide with water gives. Option A is sodium peroxide and H2, B is sodium hydroxide and H2, C is sodium hydroxide, D is sodium superoxide. So we are given sodium oxide reaction with water. So sodium oxide with water will give sodium hydroxide. So sodium oxide is Na2O reacting with water will give sodium hydroxide. And so sodium peroxide is formed from direct reaction with oxygen of sodium. So 2Na plus O2 will give sodium peroxide. And when sodium metal react with water, sodium hydroxide and H2, that is hydrogen gas, are produced. So 2 sodium metal plus water will give sodium hydroxide and hydrogen gas. So that's why when we drop a sodium metal in water, we will see first bubbles, then sodium will get ignited because of the liberation of hydrogen gas. And another reaction is sodium do not form any superoxide. So this one will be wrong. And sodium peroxide reacting with water will give hydrogen peroxide and sodium oxide. So sodium peroxide with water will give sodium oxide and hydrogen peroxide. So sodium oxide with water will be giving only sodium hydroxide. So option C is the answer. Next question is in sodium chloride, the coordination number of Na plus and Cl minus respectively are. Option A is 6 and 8. B is 8 and 6, C is 8 and 8, A is 6 and 6. So sodium chloride has interpenetrating FCC crystal structure. That means sodium Na plus cation forms one FCC and Cl forms another FCC, and both combine to form NaCl crystal structure. So first chloride forming FCC by occupying all corners and face centers, and sodium plus occupying all edge centers and body center. So you can draw the crystal structure. So chlorine in first FCC occupying all the corners and face centers. So these are the corners of the cube, and face centers. So green is chloride and blue for sodium. So sodium occupies all the edge centers and body center. These are the edge centers because it's on the center of this edge. So so in one unit cell, one more sodium is there. It's present on the body center. So sodium plus, if this is the body center, sodium is present in the body center and all the edge centers. So here we can see that coordination number of NaCl. Na plus is, so near to this sodium, we need to count how many chloride ions are present. So first one will be this phase center, so that is 1. Then this chloride is more closer to this sodium, then this one, then the next one is the other phase one, and this is the another phase, and this one is another phase. So all the chloride in the phase centers are more closer to uh, body center sodium compared to those on the corners. So there are 6 phase centers and 6 chloride ions uh, near 1 sodium plus. So that means coordination number of Na plus is 6. And next one is chloride. So if we consider this chloride, uh, so there are these sodium ions are closer. So if we expand this unit cell in one more expand this using one more unit cell above this unit cell, there will be one more sodium present here. So that will be forming an nearest neighbor to this chloride. So there will be again 1, 2, 3, 4, 5 and 6 sodium ions nearby chloride. So option D is the answer. So if we want to calculate the number of sodium plus and chloride ions in the one unit cell, we can calculate that too. So we know that corners and phase centers are occupied by chloride. So number of chloride will be, there are 6 phases and each phase will be shared by 2 unit cells. So if we place one more unit cell above this one, so this phase will be shared by 2 unit cells. So contribution of one phase center atom will be 1 by 2 because it's being shared with 2 unit cells. So 1 by 2 and there are 6 phases. So contribution from phases will be 1 by 2 and 6, and there are corners, there are 8 corners, and each one corner will be shared with 8 unit cells. So it will be 1 by 8 into 8 corners. That is 3 plus 1. So there will be 4 chloride ions in one unit cell, and number of sodium plus will be, it's in the edge center and body center. So one edge is shared by 4 unit cells. So 1 by 4 into, there are 12 edges. Plus then only one body center is there. So it won't be shared with any other unit cell. So one body center. So that's again 3 plus 1, 4 sodium plus. So coordination number of each ions are 6, and in one unit cell there will be 4 chloride ions and 4 sodium ions. Next question is lithium aluminum hydride plus ET3N in HCl will give. Option A is hydrogen gas plus ET3N plus lithium chloride plus aluminum hydride. B is lithium chloride plus ET3N plus HCl plus 0.5 L2H6. C is lithium chloride plus ET3N plus H2 plus 0.5 L2H6. and D is lithium chloride plus AlH3 and Et3 plus H2. So lithium aluminum hydride, it's a strong reducing agent, and they exist as so each H will be negative. So aluminum is in 3 plus state, so total charge will be negative, and lithium ion is compensating this charge. And we have HCl and Et3 and also. So it has a lone pair of electron. So this will be forming a bond with aluminum, so that this hydrogen will be uh, removed, and Li plus forms a bond with chlorine, and this H plus and H minus forms a bond. So totally it will be LiCl plus H2 plus AlH3 and NET. So option D is the answer. Next question is beryllium sulfate is soluble in water, but barium sulfate is insoluble in water because option is beryllium sulfate is ionic and barium sulfate is covalent. This beryllium sulfate is crystalline while barium sulfate is amorphous. Since beryllium sulfate has smaller lattice energy and a high heat of hydration as compared to barium sulfate, and D is none of the above. So here beryllium sulfate is not ionic. Actually, it's covalent. So this option is wrong. And barium sulfate forms crystalline solids in orthorhombic lattice. So this option A is wrong. And option B is beryllium sulfate is sorry. Yeah. Interchanging A and B. Yeah, this one is option B is wrong, where barium sulfate is amorphous and barium sulfate is actually crystalline, and it crystallizes in orthorhombic lattice. And here beryllium sulfate is not ionic, it forms a covalent compound, and barium sulfate is forming ionic compound. And option C, uh, beryllium sulfate has smaller lattice energy and high heat of hydration as compared to barium sulfate. So since ionic character is low for beryllium sulfate, the lattice energy is low and will have very high heat of hydration. With low lattice energy implies easy to dissociate this compound. So easier to dissociate means it will be more soluble. So more soluble implies high heat of hydration. So this option is correct. And next question is alkaline earth metals from M2 plus ions instead of M plus ion because uh, option A, M plus ions do not have stable configuration. B, M2 plus ions have more hydration energy. See, M2 plus ions carry more charge, and there IF2, IE2, secondary ionization energy values are not different from that their IE1 values. So uh, so alkaline earth metals form M2 plus ions because they have high hydration energies. Because when dissolved in water, uh, higher the hydration energy, higher the stability of ion. So option B is the answer. And next one is the series with correct order of decreasing ionic sizes. Option A, potassium plus greater than calcium 2 plus greater than sulfur 2 minus greater than chlorine minus. B is S2 minus greater than Cl minus greater than K plus greater than Ca2 plus. C is K plus greater than Cl minus greater than Ca2 plus greater than S2 minus. And D is Cl minus greater than K plus greater than S2 minus greater than Ca2 plus. So all these ions are isoelectronic. So in the periodic table, uh, S is given as S2 minus, uh, chlorine is given as chloride, and K is given as K plus, and calcium is given as Ca2 plus. So all these have same configuration as inert gas argon. So among isoelectronic species, anions have larger radius compared to neutral atoms due to low effective nuclear charge, and cations have smaller radius due to high effective nuclear charge. So we are given 4 ions, K plus, Ca2 plus, S2 minus, and Cl minus. So higher the negative charge of anions, larger will be its radius, and higher the charge of cation, smaller will be its radius. So radius order will be uh, S2 minus having larger radius compared to chloride. Then among K plus and Ca2 plus, Ca2 plus will be having lowest ionic radius. So K plus greater than Ca2. So option B is the answer. Next question is, in view of their ionization energies, the alkali metals are option A, weak oxidizing agents, B is weak reducing agents, C is strong reducing agents, and D is strong oxidizing agents. So alkali metals have low ionization energies. That means very low energy is required to remove an electron. And an oxidizing agent is the species that accepts electron, and reducing agent is the species that donates an electron. So alkali metals has NS1 configuration and has low ionization energies. So it becomes cation very faster. so it can donate electrons. So since it's donating electron, it is a reducing agent. So since it has very low ionization energy, it can readily provide the electron. So it's a strong reducing agent. The next question is among the following alkaline earth metal halides, the one which is covalent and soluble in organic solvent is option A, magnesium chloride, B is beryllium chloride, C is calcium chloride, and D is strontium chloride. So in the group 2, the order of elements are beryllium, magnesium, calcium, strontium, and barium. So while moving down the group, ionization energy decreases, ionic character increases, so covalent character decreases. So the one on the top will be having covalent character. So we are not given, we are given with beryllium chloride. So it has the covalent character and it will dissolve in organic solvents. So option B is the answer. And next one is in crown ether 24 crown 8, number of oxygen atoms are option A is 24, B is 8, C is 16, and D is 12. So crown ethers are numbered as first number representing the total number of carbon and oxygen present in the system, that is C plus O, and the second number represents the number of oxygen. So in 24 crown 8, there will be 8 oxygen atoms, and we can draw the structure. There will be 8 oxygens, and it will be connected with CH2 group. So total number of carbon and oxygen will be 2, 3. So there are total of 24 carbon and oxygen in this ring. So it is 24 crown, and there are total of 8 oxygen atoms. 1, 2, 3, 4, 5, 6, 7, 8. So 24 crown 8. So option B is the answer. And crown ethers and crown ethers are used to encapsulate alkali metal ions usually, because the ions can get trapped in between these oxygen atoms, so it will be coordinated and will get stabilized. And next question is all alkali metals dissolve in liquid ammonia, giving highly conducting deep blue solution, and why? So when alkali metal dissolve in liquid ammonia, it forms ammoniated cation and ammoniated electrons. That is, if we consider M as the alkali metal and plus ammonia, so it will form ammoniated cations and ammoniated electrons. So this M plus will be existing like uh, so the positive charge will be getting stabilized with the lone pairs of this nitrogen, and in ammoniated electrons they will be surrounded by positively delta positive of hydrogen of ammonia. So this will be the ammoniated electrons, and so they will absorb energy and excited by emitting visible radiation. So that will be giving the deep blue color, and it will be highly conducting because of the presence of these ammoniated electrons. The next question is assuming the following ionic radii in so assuming the following ionic radii in picometer, lithium ion has 74, cesium plus has 167 picometer, F minus is 133 picometer, and I minus is 220 picometer, and predict the structure type, and they are adopted by following alkali metals, LIF and CSI. So we know that with varying radius ratio rule, which is cation to anion radius ratio, we can predict the structure. If the cation to anion ratio is between 0.225 to 0.414, the structure is zinc sulfide, and if it's between 0.414 to 0.732, it is sodium chloride structure, and if it's greater than 0.732, it's expected to form cesium chloride structure. So we can calculate radius ratio for lithium fluoride. So in LIF, cation to anion ratio is 74 divided by 133, and that is equal to 0.56. So it's in this range. So it has a sodium chloride structure. In cesium iodide, cation to anion ratio is 167 divided by 220, that is equal to 0.76. So it's in the range of greater than 0.732. So has a structure of CSCl. So that's all for today. If you have any doubt, you can ask. Thank you.